Welcome to all. Now we are going to start electrostatics. In electrostatics, units of charge. So there are three system of units of charges. The first one is SI system, and second one electrostatic CGS system, and third one electromagnetic CGS system. We know that in SI systems, the charge unit of charge is coulomb. Coulomb generally represented by the capital letters. So C for Coulomb. And electromagnetic CGS system. The electromagnetic CGS system is some smaller unit of the charges. So it has the value 1. We also called it electrostatic ESU. E dot SU in a small ESU of charge. ESU of charge is equal to 1 ESU is equal to 3 into so here ESU system we have some smaller unit of charges, so we can write one coulomb is equal to 3 into 10 raised to the power 19 stat coulomb. It is called stat coulomb. Stat coulomb is the unit of electrostatic CGS systems, and it also stat coulomb. So stat coulomb is the electrostatic CGS systems, and if I calculate the value of 1 ESU of charges, 1 ESU of charge, if you solve this from here, its values comes out 1 upon, it is very smaller, 1 upon 3 into 10 raised to the power 9 coulomb. 1 ESU is equal to 1 upon, and another one is 1 coulomb equal to the 3 into 10 raised to the power 9 stat coulomb. Now third unit we have electromagnetic CGS system. Electromagnetic CGS system is a greater unit of the charges. So we generally represented it 1 EMU. 1 EMU electromagnetic EMU of charge. 1 EMU of charge. 1 EMU of the charge. This is some greater value. Now its value is equal to 10 coulomb. It has the value 10 coulomb, more than that of this one. And or we can say that 1 coulomb is equal to 1 coulomb in SI systems. 1 coulomb is equal to 1 divided by 10 EMU of the charges, electromagnetic unit, EMU of charge. So generally we prefer an SI system of units, and somewhere it is also given some problems, ESU of the charge in stat coulombs. Now next topic is relative permittivity. We generally represent it by epsilon r. It's epsilon r, and dielectric constant we represent capital K. Dielectric constant of the mediums. So these will affect the forces between two charges and the electric fields. If I place if I place a charges in a mediums, the electric fields will reduce. So in comparison to the charge placed in air or vacuum, let us suppose how it affects the medium dielectric constant will affect the forces between two charges. Let us suppose we have two charges, one is Q1 and another is Q2, placed at some distance r. So by the Coulomb's law, the forces between them is, suppose there is air, so air or vacuums have the same dielectric constant, approximately the same one. Let us suppose there is a vacuums or air, BAC for vacuums, the forces between them would be 1 upon 4 5 epsilon naught product of the charge divided by distance between. This is the force. This is equation number first. Now the same two charges placed at the same distance r in some other mediums whose absolute dielectric constant is epsilon. So the forces between them is medium. Force between the two charges when placed in the medium would be 1 upon 4 pi epsilon. We have to replace epsilon naught absolute permittivity of the free space, and we can also say that the air 1 upon 4 pi epsilon product of the charges q1 q2 divided by r square. So this is the force when charges placed force when charges placed charges force when charges placed in some medium in the medium whose dielectric constant absolute permittivity of the medium. This is known as absolute permittivity of the medium. And and this one, forces between the charges when placed in vacuum. Force in the vacuum, force on the charges placed in the vacuum, vacuums whose epsilon naught absolute permittivity of the free space, we call this one absolute permittivity of free space. Generally that value is also equal to for air also approximately. So its value is 8.85 10 raised to the power minus 12 Coulomb square multiplied Newton raised to the power minus 1 and meter raised to the power minus 3. It has the value, and we also know that 1 upon 4 pi epsilon naught, it has the value 9 into 10 raised to the power 9 Newton Coulomb square, Newton into Newton multiplied Coulomb minus 2 into meter square. So it is the value of 1 upon 4 pi epsilon naught. So this is equation number first. This is our equation number first. If I divide yes, if I divide first by seconds, we need epsilon upon epsilon naught. We should have to divide first by second. So this relation becomes, so from here first divided by second, put the value of first as the value of vacuums force between the charges when they are in placed in the vacuum divided by when they are in the medium. Now if I take the ratios between them, this terms cancelled, and what remains here, this by this. So 1 upon 4 pi epsilon naught, what comes out? 1 upon 4 pi epsilon naught divided by 1 upon 4 pi epsilon naught. If you simplify this one, so this value comes out epsilon upon epsilon naught. So epsilon upon epsilon naught known as the relative permittivity of the medium with respect to the epsilon r with respect to the vacuums or air. It also called a dielectric constant capital K. So dielectric constant capital K. So here if I find the value of what value, if I replace epsilon K times, so epsilon r times of this one, or K times of this one. So equation number 4. Now our equation number first replaced in terms of the absolute permittivity of the free air. So when the forces between the charges is placed in the medium, 1 upon 4 pi epsilon. Epsilon is removed. Epsilon is equal to epsilon r into epsilon naught. So 1 upon 4 pi. 1 upon 4 pi epsilon naught epsilon r q1 q2 divided by r square. So we can measure so our value of the force is greatly reduced if I place these charges in the in some medium. So let us suppose we compare it by using suppose these two charges are placed in waters. Water has the dielectric constant K, the dielectric constant 80. Dielectric constant of the water is dielectric constant of water is 80. So our forces is 1 upon 80 greatly reduced by 1 upon epsilon r. Here epsilon r or K is 80. So our force between these two charges when placed in air compared to the when placed in the water. So our value becomes be replaced epsilon r. Our epsilon r replaced by 80. So our force reduced, greatly reduced. It means it comes out 1 upon 80. K has the value 1 upon 80 times of 1 upon 4 pi epsilon naught product of the charges divided by r square. So here 1 upon 80 times the force in the vacuums. So our by the using of the dielectric some mediums our forces electric fields greatly reduced. Now the Coulomb's law in electrostatics. So Coulomb's has given important formula between two charges for electric forces and electric fields. What Newton's has given in case of the masses, and the equivalent to electrical equivalent or electrical analog of the Newton's law in gravitation. So we have the Coulomb's law in electrostatics. In Coulomb's law electrostatics, when two charges placed, okay, there are two charges Q1 or Q2. When they are placed at some distances, there is some forces acting between them. The forces can be either attractive or repulsive. So we have if the charges are alike, if the charges are alike means both either both are positive charges, both are negative charges. The forces between them will be repulsive. For the alike charges, the forces between the charges will be repulsive. For the like charges, if the charges are like charges, the forces between them should be attractive. So there is some important factor also. This forces is a central forces. It is center to center. If both are alike charges, the forces on A will be along this one, and forces on the charges B will be rightwards. So this would be the repulsive forces. This is known as the repulsive forces. This is a vector format. Both are equal but in opposite magnitudes. So first one, the force is the central force. Central force. Central force, it is between their center to center. And the second one, point charges should be point charges. Charges should be point charges. It is not applicable for extended body. If the charge body is extended, we cannot apply. We apply only this one. So according to the Coulomb's, this force is directly this force, whether it is attractive or repulsive, in product of the charges Q1 or Q2, and inversely proportional to distance between them. Square of the distance inversely proportional to the square of distance between two charges. It means the 1 upon r square. If I combine these two, the value comes out q1 upon q2 divided by r square. So here we have to use proportionality constant, that is 1 upon 4 pi epsilon naught, 1 divided by 4 pi epsilon naught product of the charges divided by r square. So here epsilon naught is absolute permittivity of the free space or vacuum. We called vacuum as a free space. Absolute permittivity of free space. Now its value comes out 8.85, 10 raised to the power minus 12, and its unit is Coulomb square, Newton minus 1, meter minus 2. And as a combined 1 upon 4 pi epsilon naught, in that case 1 upon 4 pi epsilon naught has the value 9 into 10 raised to the power 9 Newton meter square and Coulomb minus 2. So this is the value which we have calculated for vacuums. Generally epsilon naught has approximately the same value as that of the air. So this value is also valid for free space, air also. Air and free space is also called vacuums. Next we will go Coulomb's law in vector format. Now this is Coulomb's law in electrostatics in vector format. So let us suppose we have two charges q1 and q2 placed at distance r. Forces on, let us suppose both are like charges. Suppose both are positive charges, then the force between them will be repulsive forces. So here the charge which placed at the point of A will have the force in leftward, force on, we can write this force on 1, force on q1 due to q2 to F12. Okay, similarly force on q2 will be q2 due to q1 to F21. So this is we can say that force on q1 due to q2, and similarly F21 will be force on q2 due to charge q1. So this is the force. We generally represented using some unit vectors. So we have taken some unit vectors from charge q1 to q2, that is r1 to cap. This is the unit vectors. It goes from q1 to q2, r1 to cap. And similarly the unit vectors which goes from B to A will be r21 cap. So r12 cap is the unit vector. Let us suppose we explain this, one of them r12 is the unit vector. Unit vector gives you only the directions. Its magnitude comes out always 1. Unit vectors from charge q1 to q2. So this is the value of the unit vectors. We already know that, suppose this is a vector, say this is the vector A. If I find the directions would be given by only the unit vector. The unit vector will be vector A upon its mod. So unit vector, it has always magnitude 1. It gives only the directions. So in this way, this is the value of r12 and r21. They have indicated in the figures, the direction is indicated. So from the Coulomb's law we know that the magnitude of the force, if I find out the value of F12, here the F12, the force is acting along R21 cap. Therefore F12 will be 1 upon 4 pi epsilon naught. Its magnitude is q1 q2 divided by r square, and its direction is F1 goes from B to A. For B to A, we represent unit vector R21, R21 cap. So it in the vector format. Now equation number first. Similarly, we replace F21 in the vector format. F21 has the directions from A to B, that is along R12 cap. A goes to B. Therefore, the value becomes here F21. Force on Q2 due to Q1 will be 1 upon 4 pi, 1 upon 4 pi epsilon naught product of the charges divided by R squared. So direction is from F21 is goes from A to B. It's A to B. A to B has the directions R1 to cap. This is equation number first. So these are the formulas. We see here these two vectors are anti-parallels. So here R12 cap, R12 cap is equal to minus R21. They are anti-parallels. So that's why I have represented minus against of these ones. So if I replace R12 by R12 minus R21, this value comes out. So now F21 can be written in this format: 1 upon 4 pi, 1 upon 4 pi epsilon naught product of the charges divided by R square. And here R12, if I replace R12 with the R21, so it is minus R21, R21 cap, and minus taken is outside. So minus 1 upon 4 pi epsilon naught Q1 Q2 divided by R square, and here R21 cap, R21 cap. From equation number first, this values will be equal to, minus is outside to have the value F12, vector F12 and F21. Therefore F21 is equal to minus F21. So that F21, vector F21 is equal to minus F12. It means that Newton's third law also said that two forces when acting each other, these two forces will be equals and opposites. That is the same thing here. If Q1 apply some force on Q2, and Q2 is also apply same force on Q1, but in opposite directions, and that Newton's third law would also be verified from this Coulomb's law in electrostatics. Coulomb's law electrostatics is valid for only the static charges. When the charges are in static, in that case only the force would act between two charges. When charges are in moving, so we cannot use the Coulomb's law. So Coulomb's law is a static central forces. Okay, this is also known as Coulomb's law is Coulomb's force is central force, because it acts between the center of two charged particles. Central force. And another point is it acts between two static charges. Acts between static charges. Static means when the charges are at rest. Static charges, and the charges should be point charges. Charge should be point charge. So these are the some important facts, and next we do some important numericals for school point of view. Yes, this is the question. 2 point charges of charge value q and small q, q and small 4q, charge value placed at a distance of x. X and x by 2 from a third charge of charge value 4q. This is our 4q and q. Distance between them is x already is given. Another charge is q, which is x by 2 distance from third charge 4q. So we have to place another charges here, which is q. Q have this is the charge q here, at this point of C, and yes, charge value C, it is at a distance and at a distance of x by 2. This is x by 2. The magnitude, calculate the magnitude and nature of charge capital Q such that force experienced by the charge capital Q is 0. Here look at these charges. Let us suppose the 4Q and Q have the same positive charges. So because they should have the same positive charges, either both should be positive and both should be negative. So we can calculate the answers for both the cases for positive charges, negative charges. Let us suppose both are the positive charges. So the total forces on the Q, total forces on the Q should be 0. It means that capital Q, if both are positive, the force on Q by the 4Q which is placed at the point of A should be rightwards. So this force, suppose acting on and small q is along right side FA. So this is the force along this one, and this is capital Q, and capital Q would also apply some forces. It should have along the leftwards. Suppose the forces on the capital Q is FB. So according to questions, capital Q should be at rest. It means that it not experiencing any forces. So net force on the charges Q should be 0. It means that since they are anti-parallel, FA goes rightwards, FB goes leftwards, both should have the same values. FA magnitude also, FA is equal to FV. Now FA, if I calculate FA value of this one, FA 1 upon 4 pi, using the Coulomb's law in electrostatic, 1 upon 4 pi epsilon naught. FA has the value Q times capital Q times of capital Q distance. This distance CB also, because this is x and this is x by 2, and this should also be x by 2. Distance between CB whole square is equal to force on FB. This is the force of FB. We have to calculate the value of FA. FA has the value rightwards, and the product of charges here 4Q and small q both are small 1 upon 4 pi epsilon naught Q into 4Q divided by square of AC. So if I simplify this one, 1 upon 4 pi cancel out, and here Q is also cancel out. What comes out the value? We have Q divided by CB. CB has the value. This is again x by 2, because this is x by 2, this is x, and this become x by 2. So CB has the value x by 2 whole square, and A is equal to 4Q upon AC. 4 is small q divided by AC. AC has the value again x by 2. Here if I simplify this one, this value comes out Q is equal to 4Q. Q should have the value 4Q, and also nature. This is the magnitude amount of capital Q, and nature of the charges of Q should be positive, because if this should be positive, nature means positive. If this is positive, only then it can apply some repulsive forces on C, on the charges of Q which acting leftwards. So here its nature will be positive charge, positive Q, which comes out plus 4Q.